Thanks, Lena. I think I'm no exception in changing the title to fit nicely into the workshop. But also, I'm very grateful to the organizers for having me here and for giving me the opportunity to give this very short talk. So without further ado, I don't have a lot of time, but I just want to give a flavor of the latest things that I've been working on together with a couple of co-authors that are hiding somewhere. I cannot spot some, but they are here. And so traditionally, code-based crypto systems like Michaelis and similar make use of error-correcting codes, as we've seen in the description of Tanya earlier, and it's based on the hardness of the coding, random linear codes. And so it's important that we somehow link to the hardness of syndrome decoding problem, which is based on random codes, and we want our codes to be indistinguishable from random, which is why we study the code equivalence problem, in a sense. What is this code equivalence problem? Well, in the simplest formulation, equivalent codes, traditionally in coding theory, are codes that are possible to map via permutation. So if you can map code words to the other code words via permutation, right? And we say they are permutational equivalent. And then this notion can be extended if you use linear isometries in the following way. So instead of just permuting, we permute, and we had a scaling factor here. So you can imagine that it's a similar concept, just a bit more generic. Yeah? So here we talk about linear code equivalence, and we said that the codes are linearly equivalent. And we can formulate all this using generator matrices, like normal for the codes. So we say that two codes are permutational equivalent if there are matrices S and P, such that G prime is equal to SGP, which is kind of like the standard case. And the linear equivalence case corresponds to using a matrix Q, which is a monomial matrix. Yes, so you can imagine that you take a matrix which is a diagonal times a permutation, for example. And then this leads to the following formulation of the problem, which is the respectively permutation or linear code equivalence problem. So given two codes C and C prime, essentially determine whether the two codes are permutational equivalent or linearly equivalent. Okay, so at a glance, what is the story with the code equivalence problem? Has been studied for a very long time, and there is a proof by Petrank and Roth that shows that this problem is not very likely to be NP-complete unless we collapse the polynomial hierarchy. But at the same time, they also mentioned that the problem is not too easy, right? And as a matter of fact, there are some existing algorithms that efficiently attack the problem in certain particular cases. But under everything, the complexity is still somewhat exponential, and it's easy to find some instances that are intractable. So you can quickly come up with instances that are hard to solve. Okay? And now, of course, there is a difference here that I would briefly mention between the parameters as they are chosen usually for code-based cryptography in terms of being able to decode versus using codes that don't need to do that, actually. And this is exactly the point. Right? So could we actually use code equivalence alone to do stuff? And I will not divulge here too much about the construction of the schemes, because this is supposed to be a cryptanalysis talk. But indeed, the situation kind of recalls that of discrete logarithms, except that the action of linear isometries is not commutative. So in a sense, we're kind of a little bit more akin to the situation of isogenies, so to speak. But for example, we can adapt some existing construction to be based on code equivalence. And the selling point is that, of course, we have a big computational advantage because the arithmetic is obvious, right? It's linear algebra, essentially. So we have a zero-knowledge protocol, which we can obtain in sort of a standard way, and then we can transform this into a proper signature scheme using Fiat-Shamir with very, very good performance. It may be also possible to do other stuff, like, for example, a proper signature scheme without Fiat-Shamir following the El-Gamal framework, and this would lead to even more efficient instantiation. And maybe, what we would like to do really is to come up with an equivalent of Diffie-Hellman. Again, so this was already something very creative in the case of isogenies, and in our case, it would be even more creative, but we are certainly working on it. So what about cryptanalysis then? Well, one first thing to keep in mind is that Leon in 1982 introduced this method to find the automorphism group of a code, and it's very likely that this can be adapted to sort permutation equivalent if we focus on a subset of a certain fixed weight of code words, and then we just study the action of the permutation on this subset. And indeed, if we set this weight to say, for example, just a little bit more than the GV bound, find the sweet spot, which is big enough but not too big, then we can recover that. And the bottleneck of the algorithm is that we have to enumerate all the code words of that weight. At least this is how we, well, at the initial assessment, and I see that Antoine is shaking his head, so we may have some development. Okay, if we do that, then obviously the complexity is rather big. And this means that it's really only efficient for codes of small dimension over small finite fields. And again, it's possible that there is a more clever way to do this, right? And in fact, there is already a more clever way to do this, which is the support splitting algorithm, which was introduced in 2000 by Sandré. And this is, in fact, a dedicated algorithm for the permutation equivalence case. And here, this uses the concept of signature function, which is, in a sense, a characteristic of the code. Yeah, something that makes the code recognizable in the sense that I can map the code and a certain position to the permuted version. And I say that the signature is fully discriminant if this is true. So whenever I change positions, I never get a collision. And so, of course, if I'm able to find a fully discriminant signature, then I can efficiently distinguish the code. Yes. So what's the difficult part here is that finding a fully discriminant signature is not obvious. And the thing that Sandré proposes to do is to build the hull of the code, which is the code intersected with its dual. And then you can do some fancy stuff. You can puncture and compute the weight enumerator, and then essentially you're able to compute such a you can find such a fully discriminant signature there. And the complexity scales accordingly. And you see that the dominant term here is this, not the linear algebra, right? But is the Q to the dimension of the hull. And interestingly, so this hull, and I think Tanya said a couple of things about this. It's for typical cryptographic parameters, it's rather small, right? So this is efficient when the hull is small, except for the case when the hull is actually empty. This case was studied recently by Bardet, Othmani, and Said. But if the hull grows really big, then this algorithm is obviously exponential in that, right? So the worst case in this scenario is weakly self-dual codes, which the dimension of the hull is maximum. Yeah. So essentially the algorithm makes the case intractable if we use weightless self-dual codes. And now we're talking about permutation equivalence, but in fact, the case of linear equivalence can also be solved if we start working on the closures of the code, which is this following notion. So the closure of a code is essentially the code seed, which we have exploded, right? Using our alphabets, we get another linear code, which is long n times q minus 1. And then the fundamental point is that if the two codes are linear equivalent, then their closure are permutationally equivalent, and vice versa. And so, in fact, solving linear equivalence corresponds to solving permutation equivalence on the closures, which means we can do the previous things that we were doing on the closures, right? So for Leon, we will enumerate the words of the closure. And for SSA, we can actually run this on the closures because this solves permutation equivalence. But Sandré showed that when q is greater or equal than 5, then the closure of a code is always weakly self-dual. And this is exactly the case we're interested in. Because then we can take codes which make SSA not applicable. What about the quantum? Because this is, after all, a quantum cryptanalysis workshop. So first of all, there is Grover, right? And we can imagine to apply Grover to Leon's algorithm, which is a search algorithm fundamentally at its core. And we can at least imagine the usual speed up, right, in the search part, at least. For SSA, well, if we try to do a naive Grover search over all the possible secrets, then this will not outperform the classical one, just because of the size of the things we're searching. But we can also think of using Grover within SSA. And so this would roughly correspond to trying to find this function here, which is defined as with the signature function, and try to see when this function is 1. And well, in this case, the search space is quite short, actually, because you're just looking for the index between 1 and n, right? But the oracle is expensive. And so, again, the complexity becomes pretty big. And this, again, does not outperform the classical SSA. So for SSA, actually, Grover does not bring any benefits. And what else can we try to do apart from Grover? I mean, Grover is kind of like the standard go-to thing, but another thing that we can do and is popular is quantum Fourier sampling, I guess, right? So in our case, we could search for this secret subgroup H, and G is given by this, where we take invertible matrix here and permutation, right? So the usual situation. This was an article by D. Moore and Russell in 2011. And well, the article is actually making some advertisement, but all we can say really is that in some cases we can derive an upper bound on the sampling probability to find this. But this is not really a criterion. Yeah, it's not really guaranteeing any form of hardness. First of all, well, we could have some codes that are still possible to attack by classical means, even if they satisfy this criterion. Yes, and so it is not a guarantee of weakness or hardness in either way. So this is as much as has been done in terms of applying techniques of quantum Fourier sampling in. So essentially, it's just showing that Shor's algorithm is not going to help us in this case. Yes, so it's not exactly a very useful result. But this is all we have. So anything more that we can have on the quantum side of attacking a Code-Equivalence problem would clearly be a benefit for us. And this is all I have, because I think we're also already a little bit late. So I'm happy to take questions, and thank you for your time.
Please, it seems like the definition you used during the talk was only for Hamming metric, right?
Yes, it's for Hamming metric typically. I mean, yes. Mm-hmm.
And if you change the metric, like round metric, is there some result about Code-Equivalence?
So, I mean, I think we're just talking really about the. Yeah, I mean, I don't think it makes any difference, right? It's the same. I mean, I'm just talking here about the code as a algebraic object and mapping to another code. We're not actually measuring weight of the code words or